I would have liked to have seen your reaction when you found out that we were going to be talking about domain and range. Definitely a topic that goes back to algebra, but I want you to know that it's a topic that goes beyond algebra. It's something that, if you keep taking math, will pop up often, and so we want to understand it. We're going to think about how to find a relation's domain and range. And let me remind you that that is really just a matter of thinking about the x and the y values. Let me encourage you to think about what x or y values you think are represented by each of these graphs. Try this as a little bit of an activator, as a warm-up, and then we'll follow up on it. Now, when you look at this graph, this first graph that we have, perhaps your eyes focus on different numbers. If your eyes, or I should say, focus on different places, if your eyes sort of noticed or focused on this spot right here, I would say that that definitely can be helpful. It just depends on how we use it. Now, that spot right there, that's actually a point. That's the point -2, 0. But in particular, it's the furthest point to the left. It's the furthest x value to the left. And so we can begin to kind of hone in on the x value of this point, of course, -2, and we want to understand that it is actually the starting point of all the x values of this graph. Do you realize that the x values start at -2, but then start to proceed to the right? Likewise, if we look down here, we come up with the same conclusion. The x values that start at -2, but then go to the right, would be the domain of this graph. And we can write that by using different notations. If we choose, we could use interval notation. We could say that we're starting at -2, we're going to the right, we're going to infinity. How about the y values of this graph? Sometimes that can be a little more challenging for students. Where do you look? Do you look at this point again? Well, if you do you understand that that's just a y value that, if you will, is in the middle of the graph? Because here's a y value that's higher. Here's a y value that's higher yet, and yet. In fact, the truth is, each of these blue dots has a y value that keeps getting bigger and bigger. It's going to eventually go to infinity. If you look down here, the y values go down. In fact, they keep going down. Eventually, they're going to go down to -infinity. You see, every y value is shown on this graph eventually, not just starting at 0. The truth is, the y values start at -infinity. They go to positive infinity. Some students would say that the y values, that all y values are shown on this graph, and that is definitely a true statement. How about our second activator graph? Where did your eyes take you, and what did you do with that place? Most students would say that they naturally kind of noticed this spot, this point. Yes, it's the point 1, 1. But again, I ask you, what are you going to do with that? First, if you're going to think about the x values of this graph, then, well, we want to just focus on the x value of 1. And then understand that, yes, we could call that the starting point of the graph, but what other x values are shown? Let me suggest a interesting strategy where you can actually go sort of, if you will, reference the x-axis as you think about additional points on this graph. What I'm doing here is I'm really just taking points that are on this graph, but I am then referencing where they would fall on the x-axis. These arrows that I'm drawing down here are really just trying to help you see that the x values of each of these points seems to be highlighting this part of the x-axis. And we say this part, we mean the part that is going to the left. The part that's going to the left of x equals 1. Now, yes, we can say that 1 is the starting point, but perhaps it would be better to really call it an ending point, because we always want to use the smallest number in our interval first, followed by the bigger number. Again, the number 1 is actually my bigger number, understanding that this graph, if it's going to the left, is actually going or starting at negative infinity. How about the y values of this graph? If you use this point that we have already referenced, it has a y value of 1. Now, what other y values start to show up on this graph? If I reference the y-axis, if I kind of draw arrows to the y-axis, from any point on this graph, are you starting to see what parts of the y-axis are being highlighted? The truth is, it's all these parts here and continuing to go upward, but more importantly, it's actually, the reality is that the bottom of this interval is actually this height, or this y value of 0. And so if I go back to my y value of 1, I kind of can argue that it wasn't helpful. Rather, it was a y value of 0, if you will, the bottom of my graph, that became the most important point. It's like a starting point. Because it's a starting point, I can use it in my interval notation, then saying that the graph is going to go up to infinity. Now, each of these answers up here also represent the domain and range, because that's what domain and range ultimately is. It's the x values represented by a graph. It's the y values represented by a graph. And when we talk about the x values of a graph, we're also thinking about the horizontal movement of the graph. And additionally, there's a time where we call those the input values. When we talk about the range of a graph, those are the y values. And of course, they represent the vertical movement of a graph. And there's going to be a time where we talk about the range as also being the output. Often when we're talking about domain and range, we also throw in a quick conversation on basically function or not a function, or as it says here, just a relation. So as a little reminder, a relation is really just any mapping, or when x values simply map to y values. Now, some students say, what do you mean map? The word map really is another word in math for connect. And that's often what happens with any problem. X values will connect to y values. The interesting thing is, though, we say it's a function, that's actually a special mapping when each x maps to just one y value. And when each x maps to just one y value, we have a function that also satisfies the vertical line test, which we often abbreviate VLT. But again, if it's a function, it's going to satisfy the vertical line test. This is honestly a separate conversation, but it's often thrown in with domain and range. And we can go back up and we can notice pretty quickly that this graph here is not a function. And there's all kinds of ways that we can notice this. Maybe the easiest way is to just notice that the number 2 maps to a y value of 2, but then at this point, the number 2 maps to a y value of -2. Now you see, that would not be a function because the number 2, the red 2, mapped to different y values. Instead, it would just be considered a relation. But we would say again that this first graph is not a function. Additionally, if you draw a vertical line, it's going to touch at 2 points, which means it doesn't satisfy the vertical line test. On the contrary, if you look at this second graph, even though it's kind of a special graph, that it has this endpoint, the truth is that every x value along here only connects to one y value. This x value of 1 only connects to a y value of 1. This x value of 0 only connects to a y value of 0. Now this x value of -1 happens to connect to a y value of 1, but the important thing is that it still only connects to one y value. In other words, it's okay if I share y values as long as it's only connected to 1. And we would say that this graph is a function. Let's practice domain and range and some function talk with a few more examples, like example 1. Now, when you think about the domain of this graph, you want to think about what this graph is doing horizontally. There really aren't any points that seem to represent a starting point. If I think about this point in the middle, it's not that the graph necessarily starts there. As I hope you can see, the graph actually goes to the left and to the right from that point. The reality is that this graph goes to the left and to the right forever, and it ends up touching every x value that is between -infinity and infinity. We just need to say so. There's actually no restriction to that domain. But the range is a different story. The range, you want to more think about the vertical movement of this graph. You should feel like vertically the graph never goes higher than this dashed line, nor any lower than this dashed line. There's no graph up here or down here. That would mean that my range is only in between 1 and -1. And we just need to say so. We need to say that the range is between -1 and 1. Now, is this graph a function? Does every x value only map to one y value? An easy way to tell is by drawing vertical lines, and each of these vertical lines, as you want to notice, is only touching the graph at one place. That means it satisfies the vertical line test. That means it is a function. How about example 2? When you think about the domain of this function, maybe you're searching for like a starting point. If your eyes go right here, that's fine. You want to understand that the graph actually proceeds everywhere to the left as it gets closer and closer to -2. But the truth is, if I go up here, even though it's an open circle, I should say that the graph then picks up where it left off at -2 and proceeds everywhere to the right. If you draw lines to the x-axis, you will quickly realize that eventually you touch every point along the x-axis, including -2, including everything to the left of -2, and including everything to the right of -2. We're trying to make the argument that this graph has no restriction on the domain. It goes left and right forever. When it comes to the range of this graph, we're thinking about the y values. You should notice that the y values on this part of the graph only ever equal 2. But the y values on this part of the graph only ever equal -2. There are no other y values that this graph uses. And that means that the range of this graph is going to only be 2 and -2. Now, a way that we can write that is using that set builder notation from the other day where we say all y such that, well, y will only equal 2 or -2. Is this a function? Does every x value go to just one y value? Yes, it does. There's no place on this graph where an x value uses 2 different y values. Now, our last example is an equation. And one may ask, where's the graph? Which is a great question and kind of leads us to our method, which is to think about or maybe to go find the graph. Now, the place that you find the graph may be using a piece of technology, like I'll show in the classroom, using a calculator that can graph it, or maybe even using a computer. I don't want you to worry about that right now. What I want you to understand is that we need a graph to be able to see the x and y values. And what we end up seeing when we graph this is a semicircle. Now, it's a semicircle that would have some points of importance. In fact, your eyes would most likely, not -3, but +3. Your eyes would most likely kind of start at these points or maybe notice these points. It turns out that it's a semicircle that has a radius of 3, which is why each of these points is as given. What x values does this graph show? Do you notice that the x values don't go anywhere beyond -3, or in the same way don't go beyond +3? Another way to say that is the x values are all between -3 and 3. What y values does this graph show? If you feel like that the top of the graph is restricted by +3, you're right, but where's the bottom of the graph? Isn't it true that the bottom of the graph is restricted by y equals 0? Now, I circled both of these zeros. It doesn't matter which one you think about, because the truth is the bottom of the graph is y equals 0, the top of the graph is y equals 3, and we just need to write that as the restriction. Yes, it is a function. It passes the vertical line test. If you draw vertical lines, you will only ever touch at one point. Now, each of these examples were different, and that is on purpose to continue to give you as exposure to as many different situations as possible. But now what I would like you to do is I'd like you to go find the digital Desmos activity. You'll have to grab the link off the calendar, and I want you to walk through each of those examples where Desmos is going to give you an opportunity to sort of visualize a little bit more the x and the y values using some of the tools and apps that are in that activity. Now, once you finish, you'll want to start the video back up so that you can try practice 1 and practice 2. In class, I would actually initial these for students. On the video, the best I can do is just give you continue to give you some instruction and some feedback on how to find them. So do the Desmos activity, pause the video, and then come back and try practice 1 and practice 2. At that time, I will then go over them with you. So what do you think about the domain of practice 1, the domain? After doing the Desmos activity, if you really just reference or even draw or notice these two boundary lines, x equals 0 and x equals 2, that is good enough for us to be able to say that the domain of this graph is between 0 and 2. In a similar fashion, after the Desmos activity, if you kind of draw these two boundary lines and you say that the entire graph, and you reference y equals 2 and y equals negative 2, then we can say that the entire graph is between 2 and negative 2. And that would be the y values for the range. Now, did you notice I made a mistake on the way that I wrote this range? And I can't say that I did it on purpose, but it's something we can learn from. I actually wrote the higher number followed by the smaller number. That should feel a little bit sort of backwards to you. You always want to write the smaller number than the bigger number. So really your range is negative 2 to 2. How about the whole function piece to this? If you start drawing vertical lines, you might argue that it only touches at one point until you draw your vertical line the whole way through the graph, at which time you notice that it actually touches at 2 points. And in fact, there's another vertical line and there's many more. But as long as there's one vertical line that sort of fails the vertical line test, you're able to stop and say this thing's not a function right away. Practice 2. The domain. The x values. Now it's pretty easy to say that the x values are these circled numbers, but how do you write that? Well, two things. You write it using roster notation, and the second thing is you do not repeat. You do not repeat the number 0 because it's already in the domain. It's already been written. So your domain is just 0, 2, and 1. Now, I would say that what I wrote here is correct. It might be nice to write it in chronological order. You wouldn't get marked on that, but typically we record things chronologically, so I'll go ahead and change that. How about the range? It's the y values, right? Well, if you look at these y values, the lowest one is 2, the next one is 3, 4, and then all the way to 6. So we'll write them chronologically. Lastly, when it comes time to think about the function, not a function, we would want to, at some point, notice that 0 is mapping to 3, and then we turn around and say that 0 is mapping to 6. That's can't do that. This is not a function because the number 0 is mapping with 2 different y values. Try the homework on the back as you continue to explore domain and range.